Okay, let's start what, according to me, will be the main 3D IC driver. Now, I guess there will be as many IC drivers as there are applications in the future, so you can pick yours, but I pick mine, and I truly believe that mobile computing is going to be the main 3D IC. High-definition, real-time high-definition video encoding requires about 13 gigabytes per second of bandwidth between the processor and the DRAM memory. Now that's really a lot, and there is only one way to do that in a mobile system, and it is with TSV connected logic memory solution. Okay, TSV connected logic memory system. What type of TSV would be like to be able to have a technology that decouples the via diameter from the wafer thickness? Because the ability to decrease TSV diameter without affecting the wafer thickness has a huge implication for how much die space is available for working circuitry and for the overall cost impact of the TSV adoption. This is a plot that charts the amount of silicon area that you have to dedicate to TSVs and also the related cost as a function of the via diameter from 12 micron all the way down to 3 micron, and conversely, if we keep the TSV depth constant, we have the aspect ratio going from 4:1, 5:1, all the way through to 20:1. So, if there is one thing that I would like you to put in your pocket when you go out of this chart, is actually this one. Basically, for any given aspect ratio below 10:1, you are bound to pay more than 1% of your precious silicon area, and that translates into a cost of more than $100 per wafer. Anything less than 10% will cost you more than 1% of your wafer. That's a lot. Let's see how people are suggesting to tackle this TSV process first. So first thing first, we have to isolate the silicon from the metal that we're going to put into this TSV. There are two ways of doing that. CVD, chemical vapor deposition. Well, that's a high temperature process, so it's not compatible with memory applications that requires lower temperatures than that. And also, this step and the subsequent steps do require smooth walls. And that has an impact on the speed at which you can drill the holes. Basically, the smoother the wall required, the slower the drilling the hole is, and therefore the most costly that hole drilling step is. Alternatively, you can grow the oxide by cooking the wafers, thermal oxide. Well, this is very high temperature, so it is dedicated to silicon interposer only. Let's have a look at the barrier. You have ionized physical vapor deposition and or chemical vapor depositions, but our own experience is that for any aspect ratio approaching 10:1, but below 10:1, you do have this continuous field very close to the bottom of the via, like the picture that you're viewing here. That's a discontinuous barrier. Also because, even if you can plate it continuously, then you have to clean it with a plasma cleaning step, which are highly inefficient. Basically, they are not able to go and clean the bottom of the via for any aspect ratio larger than 5:1. Well, then you say, we can use atomic layer deposition, and they are very conformal. Yeah, that's correct. But they are, again, high temperature process steps, and at extremely low unit power, extremely low throughputs. The main message of this slide. Do you see how patchy a solution is this? Where is the top-down approach? Where is a long-term strategy in tackling what is the most fundamental element of the 3D IC revolution? That's a TSV. It's just patchy. Take what is there and try to push it to its limit. Dry process 300mm TSV wafer, cost of ownership. We have people telling us that it is possible to have it as less than $120. I'm going to show you that this is wrong. Just take the list of all the process steps required to make your TSVs, metallize them, thin the wafers, making the distribution layer on the back side, putting the bumping, and bonding the two wafers together. This is a total of 28 steps. You would require 34 different machines. You go call your suppliers or ask your friends on the floor what the cost of that would be to buy one single tool, new tool for each step. You are looking at a minimum capex of 70 million US dollar if you want to do that. So if you consider a depreciation of 5 years and a 10,000 wafers per month production, that converts into an equipment depreciation cost of 120 US dollar wafer just for that cost item. Now you all know how a cost of ownership calculation must be made. To that cost item you have to add all the rest: consumables, maintenance, hookup cost, utilities, labor cost, overhead, footprint ratio. So if you do the math, this is the real number. If you go dry, you are bound to pay more than $250 per wafer. Oh, and by the way, to get watts, aspect ratio 6:1. I find this a bit depressing though. Cost-effective, scalable, wet process TSVs. There are solutions out there today that can easily deliver more than 20:1 aspect ratio at a significantly reduced cost. Those, I cite one, provide polymer-based isolation, a nickel boride-based barrier, and a directly plated copper field on barrier. And they provide, as I said, high aspect ratio. They are highly conformal. They have strong adhesion, high step coverage, and the film properties, I've already shown this in several conferences, match or exceed those of dry processed films. Picture of several wet isolation and barrier films deposited on TSVs ranging from 10:1 all the way to 18:1, with TSVs as narrow as 4 microns. And look at the right-hand side, the undercut via mouth. We can coat that without any problem with step coverage of 70% for both isolation and barrier. And then we come with fill. We have developed a high purity copper fill dedicated to narrow, high aspect ratio TSVs like the one you're looking at right now at 2.5 by 25 micron. High purity chemistry, direct plating on barrier, no chemical degradation of underlying layer, no need for hot entry, and seamless integration of complete wet process TSV metallization module. What do we have to propose? Well, a 3x or 5x reduction if you go wet. It does pay to do it wet, because basically this technology is sensitive to aspect ratio. It took me a long time to write this last slide because I said, hey, here we have competition, we have the current establishment that is trying to apply an incremental evolution of existing equipment to solve a revolutionary problem. And here there are solutions that are actually revolutionaries and that are just starting to be integrated. So how can I conclude something that is really just starting? That doesn't really make sense. So there is no conclusion, and actually I would like just to leave you with what I think is an appropriate quote of Thomas Edison. Thank you very much.
Thank you, Claudio.